This time around, I actually have given you what the Laplace transform of such a power expression is. And I do think this is going to be a true statement as long as n is any natural number or 0. Now, I've got a stipulation that s has to be strictly greater than 0, but I'll show you where that comes to play in the proof. So, list my choice of words carefully. Laplace transform of t to the n is equal to this for all natural numbers n, but it also works when n is equal to 0. Now, if I'm going to prove a mathematical statement that's true, when the statement is based on some subset of the integers, then because, again, we're all pre-calculus experts, you know where I'm going with this. I'm going to construct a proof using mathematical induction. So in using mathematical induction, I guess my very first step is, of course, to show this works for the small such value of n. That would be 0. So if n is equal to 0, let's see what's happening. Then the Laplace transform of t to the 0 power is just 1. I don't think I said that correctly. The Laplace transform of t to the 0 power is the Laplace transform of 1. But here's my definition. This improper integral. Where in this particular example, that function f is simply 1. So there is the simple improper integral I need to evaluate. To do that, I will, in my usual fashion, rewrite the improper integral as a limit of a proper integral. And now I anti-differentiate that expression in the integrand's position. But I do think it's going to give me this. So I do think, yet again, I'm in a bit of trouble. I really don't know what's happening with this particular term as x increases that bound. It all depends on what s is. So if s is negative, notice that this exponent is positive x. And as x is increasing without bound, I think that first term increased that bound. Therefore, the improper integral diverges. But check out what happens if it's the case that s is strictly negative. I think I misspoke, sorry. Check out what happens if s is strictly positive. This exponent is negative x. And of course, as x increases that bound, e to the negative x is going to go to 0. So I think in the end, all I'm really left with is 1 over s if s is strictly positive. So that being the case, with this mathematical statement up here, I've shown that it's a true statement if n is equal to 0, because that 1 over s can be interpreted as my 0 factorial over s to the 0 plus 1 power. That's just my 1 over s. Oh, but shoot, now here's where all the work comes in. The second part of my proof of mathematical induction is a bit more sophisticated. So allow me. So with the second part of my proof of mathematical induction, I'm going to assume this statement right here is true for some value of n, albeit I don't know what value that is. And if I assume it's true for some value of n, call it k, and I can show that this statement is true for the next consecutive natural number k plus 1, then I think by mathematical induction, I've shown that this statement is true for all values of n in that set. So here we go. I'm just a little worried because I can hear my cat Pythagoras is destroying something downstairs. So we will show that the statement on the other side of the board is true for the next consecutive natural number. That would be k plus 1. Of course, you'll see here too, it's only true if s is strictly positive. So here I go. To show that this is equal to this, let's just start off with our definition. So blindly, my definition of Laplace transform says the Laplace of that beast is nothing more than the evaluation of this improper integral. Now, I'm not going to massage this beast without first rewriting as a limit of a proper integral. Now remember, I made an assumption. The assumption is I know what Laplace of t to the k power is. So to force myself to see the Laplace of t to the k power somewhere within this limit, or somewhere in this expression, I should say, let's just do an apply integration by parts to reduce the order of the second factor. So how can I do that with this board space? Do you mind if I waste a little bit of time? I'm sorry. I'm not changing anything. I just need more space. So here we go. I want to reduce the order of the second factor. So clearly, I'm going to allow u to be it. And therefore, dv be everything else. And pay the consequence of my actions. Differentiating. Anti-differentiating. So within this limit, I will now apply my integration by parts formula, which says the integral of my u dv is equal to u times v minus the integral involved my v du, but that's going to have a coefficient out front, which is negative k plus 1 over s. And in the integrand's position, I have this times this. I'm getting a little worried. I need to do some more board space. This times this, I've already taken care of the coefficient. That gives me e to the negative st times t to the k, if you don't mind. Okay, it's time to take a break. And again, if you can just forgive me, since I'm the one who actually has a limited board space. Would you agree that if you evaluate this thing right here at the lower bound of integration, that there right there is going to be 0. The whole thing drops off to 0. And so I just need to worry about what happens when I evaluate at the upper bound of integration. That is to say, when t is equal to x. Now give me this. Of course, with that negative exponent, I can force it to be a positive exponent by throwing that factor downstairs. Now that this exponent becomes positive downstairs, can you appreciate that this limit, excuse me, the limit of the second factor right here, of this first term, can be easily evaluated just applying L'Hopital's rule k plus 1 times. And if I apply L'Hopital's rule k plus 1 times, doesn't my numerator become this? My denominator becomes this. Oh, was that too low? No, I think you can see that. Now, the only variable expression is the second factor downstairs. And so as x increases that bound, I think this entire term right here is going to go to 0, assuming s is positive. And so if you don't mind that little bit of hand waving, only because of my limited board space, I do think this whole first term is going to go to 0. And that being the case, look what I have left over. I've got the limit of that constant times that improper. I've got the limit of that constant times that proper interval. If I pull the constant out, now look what's left over. Here too, a little more hand waving. The limit of this proper interval. But it's not just simply this. But yet again, I made an assumption that right here, that being the Laplace transform of t to k can now be evaluated at something you might not be able to see. It's a little too low on the board. So take a peek at how I made the assumption. This is nothing more than that. So with a tad bit of erasing, oh, Pythagoras, what you doing? I think I'm left with a k plus 1 over s times Laplace t to the k, which I assume was equal to this. Or shall I say better yet, upstairs, would that be a k plus 1 factorial? And downstairs, let's see, downstairs, is that going to be adding these exponents? Will that give me an s to the k plus 2? Oh, and shoot, that's exactly what I wanted. Therefore, by mathematical deduction, I have just proven to you that Laplace transform of t to the n is indeed equal to n factorial all over s to the n plus 1 power, where n is an element of the natural numbers union with a single set of 0. And of course, where is the case, if you can read that, my goodness, that s is strictly positive. I have just proven what I wanted to show. Boy, is that a test-worthy question. I like it.